In fact, this is my very first time to give a talk in a robotics conference and workshop. So let me just briefly introduce myself further. I'm mostly working on computer vision, especially the 3D computer vision and 3D human motion field. These are some of my and my colleagues' previous work. We have been building this Panoptic Studio multi-view system, and we made some interesting progress in 2D and 3D human pose estimation field and 3D human digitalization and so on and so forth. So let me start my talk with this example video with a question about how humans move the way we do. I think the first reason is to accomplish some physical goals, such as moving something, manipulating tools, and so on and so forth. And one very interesting thing is that as a human, we can very easily manipulate any unseen tools in unseen environment, which is quite difficult for robots yet. And maybe the second reason of human motion is to transmit some communicative signals. And in these cases, we basically move our body to send some messages to others. So, but using body proximity, facial expressions, and hand gestures, basically we convey some of our messages, intentions, and emotions, and so on. And these are very easily decoded by other humans. Again, this kind of way this kind of human motion is very hard to teach for robots as well because we don't even know how we are doing this kind of thing. So the main challenge here is how we can teach this kind of manipulation skills or communication skills for machines. That's basically the main challenge. And this is not just due to the hardware problem, even implementing that in virtual environment by making some virtual humans for human-like human motions, that is still a challenging problem. So my research goal is basically to endow machines with the ability to perceive and imitate human behaviors. And I do that by leveraging data. So the main question is how to obtain and represent and use this kind of data. And nowadays, this is a really interesting time because we have seen lots of success in other modality field, for example, in language domain and image domain. And obviously, the major ingredient of the success is basically the availability of a large-scale data set. But the question is, what about the human motion data so that we can teach machines to behave like humans? The problem is, compared to this language or image data, as we all know, capturing human motion is very tricky problem. So how to sense group of people, how to handle occlusions, how to sense this coarse human motion as well as very subtle hand motions. All this thing is very challenging problem. So during my PhD time, I tried to build this system with my colleagues. The name was Panoptic Studio. Unfortunately, the system is gone, but it has about 500 sensors so that we can cover some spacious places so that we can capture the motions from multiple people without using any markers. So it's kind of markerless motion capture system. So for example, the output of the system is something like that. So you can capture the body motion and finger motion like that quality. And using the system, we have collected some amount of data when people are doing some very interesting social communication so that we can capture their face, body, fingers all together. And as we know, there have been several other interesting data sets available publicly. But the problem of this existing work, including ours, is basically they are not large scale yet. They are basically studio setup. Most of them are just human only without human object interaction, although there are some interesting data set nowadays. They do not have finger motions, for example. And the bigger problem here is the amount of data we have collected so far is at most less than 200 hours, which is not super large scale yet. So what would be the next goal of our community, maybe both vision and robotics and all these people? So we really wanted to pursue to collect a large scale data set, hopefully in the wild situation. We want to more focus on human object interaction because that is somehow unexplored area. And at the same time, we want to collect them in a high resolution, including finger motions. Maybe one possible way of solving the problem is just collecting the data from internet videos by measuring 3D motions. Indeed, we made progress. We have some available monocular motion capture method, including our front mocap. They're just a better methodology nowadays. But still, this problem is not super accurate yet, especially when the person in the scene is interacting with the world. So today, I'm gonna very briefly introduce our new effort in two different directions. The first direction is a lightweighted mocap system for long-term indie wild capture. So let's get into the first part first. The paper name is mocap if, has been published in the CVPR by my amazing student, Zia Lee. The goal of this system is basically we want to capture some casual human motion in our everyday life. So basically 24/7 for a long-term large-scale motion collection. And one possible way of doing so is via maybe wearable mocap. But obviously the problem is the mocap system is expensive. And it's inconvenient because we need to wear either mocap suit or we need to attach IMU sensors, maybe more than 10 IMU sensors on the body. Compared to that, our system is actually very simple. We only need two smartwatches, one for each wrist, and one head-mounted camera. So you can see some examples set up on the left. And on the right, you can basically see, a third-person view of the person who is wearing this setup, which looks just natural. At the moment, we are using GoPro camera for the head-mounted camera, but that can be replaced by any glasses type egocentric camera. And the output of our system is to get the full body motion capture, including the leg motions and so on and so forth. And obviously, this is hard problem because the input of our system is very sparse, just egocentric videos and also IMU signals, which only captures some temporal movement of the wrist. So main idea of our system is actually the following. I'm gonna very briefly get into there due to the time limitation. So first, from the videos, egocentric videos, we used off-the-shelf SLAM method so that we can get the point cloud and the head-mounted camera's positions, basically. And this camera position provided some clue of head orientation and position. And at the same time, we leverage this IMU signal that provided some temporal information, no absolute information. And we use both information. And in the end, we apply some sequence-to-sequence regression method to infer the full body motion. One systematic challenge here is the point cloud and camera pose and IMU signals are from basically different coordinate system because they are from different modality. So we need some initial alignment process, calibration process to have the same scale and same orientation. And after that, the later problem is more or less regression problem. But again, this is also challenging because of the ambiguity we have from the input data. For example, on the right, you can see the person is standing still and sitting still. But when you actually observe the IMU signal, they're absolutely the same because there's no motion from the wrist. One cue in our method to differentiate this kind of ambiguous status is basically the height of the head, because obviously in two situations, the height of the head is different. But to compute the absolute height of the egocentric camera, basically we need to infer the full level first so that we can compute the height. And we also use the absolute up vector of the head orientation as additional input. So the basic kind of contribution of our method is to infer this full level so that we can include the height information as well in the input. So in the end, we just concatenated all these clues as input, and we trained a regression model so that we can infer this full body motion. For that, we used the mocap data set by emulating the IMU signals from the full body mocap and use that as input data. We use this transformer-based sequence-to-sequence model, but again, let me skip this part. And again, to infer the head height, we need to regularly fit the floor plane so that we can infer the height of the person as the additional input. if we actually see the quality of the leg motion, it's quite decent because the wrist motion and leg motions are quite well correlated. But when you actually see the manipulation task, in fact, the localization of wrist is quite challenging problem because IMU signals only provided the relative pose. One clue we additionally use is the egocentric camera's scene, because usually during the manipulation task, the people tend to see the hand as well, so the hand's part can be visible from the camera side. So we use some additional refinement for that. Let me skip the details, sorry. So this is the final output. On the left, you can see the egocentric view, and on the right, you can see the final output. In fact, the person is moving around pretty large space, the campus space. You can see the bird eye view on the bottom, and you can see the full body motion as the output of our method. This is some example of manipulation task. Again, this is harder because they're just more ambiguous situation. This is another example. A bit more interesting scenario is multi-people capture. So in this setup, we ask people to wear the same setup, two Apple Watches and one egocentric camera, and we can apply our method for individual person. Basically, we can place all of them in the same space because the cameras can be posed in the same order space. One interesting additional information is when they are interacting, maybe each individual's camera can see another person. Assuming those visual cues can be shareable each other, we can additionally use that for the further refinement. This is another example. Okay, so that was the first part of our method to collect some long-term, large-scale indie-wild motion capture via some light-weighted mocap system. So our final hope is maybe we can distribute it. We can distribute this kind of mocap system for 100 people and ask them to collect maybe hours or days or months of their data, from which maybe we can do some interesting processing. And let me jump to the second part of my talk that is about our para home system. And this is a little bit orthogonal system. So we actually built a indoor mocap system so that we can capture some human object interaction scenarios. This has been done by my another set of amazing student. So these are some example output. So we actually built a home style environment where we have actual the electric devices and furniture from which we can collect basically human motion, human hand motion capture. And also importantly, we can also capture the object motions as well, their rigid motion. And if the object are something manipulatable, we can also capture their parameters. So everything in this space are in a parametric space, in 3D parametric space. So the goal of our problem system is to pursue to capture some real-world human object dynamics, particularly in a room scale environment. So instead of, manipulating with single object, we wanted to have more realistic setup so that people can play with multiple objects in a more casual kind of scenario. So let me show you one example. This is the output with the instruction, put the sliced food into a pan. And as you can see, the person is interacting with multiple objects sequentially. And these are more other examples. So compared to some interesting existing setup where people try to focus on human object interaction is in grasping kind of setup, in our cases, our data set captures some interaction with multiple objects. They're sequential basically, so they have some storyline given the same instruction, and those kind of correlations can be captured from our system. So in summary, our system has human object interaction in a natural room setting. So it focuses to capture dexterous human manipulation and body motion, as well as multiple articulated 3D objects. People can actually freely move around the room, so it also contains a navigation naturally. Sequential manipulation scene. Importantly, each action has been annotated with text description so that we can try some text to 3D motion kind of direction. So far, we have collected more than 500 minute data set. These are not available yet, but we are making our final step to release all of them within this month, hopefully. The example sequences has been already released, so you can try. These are the example view of our system. We have LED light, we have cameras, we have 70 cameras. They are for tracking the object basically. And basically our goal is to capture the reliable human body and motion, hand motion. For that, we use this wearable suit and gloves because they are basically occlusion free. And but for object tracking, we use this 3D markers so that the 3D marker can be seen from multiple cameras for reliable object tracking. These are the views from 70 cameras. And very importantly, we also scan the 3D object altogether so that we can have complete 3D world. We also made all this animatable or manipulatable object into parameter models. So they are basically recorded in the parametric space. So the parameter captures the angle of the cover or door. Some objects have two parameters because they have two door, and we collect those kind of motions during the human object interaction. Our object tracking is quite straightforward because we can track the 3D marker. So the object location relative to the 3D marker has been already there. So we can only replace the tracked markers with the object location like that. And one systematic challenge of our method is that basically we use two different tools, systems for human motion capture and object capture. So we need to basically align their spatial and temporal unit. For that, we need some calibration process to handle those kind of different modality. So on the left, you can see the raw output from body mocap and object tracking. And on the right, you can see the calibrated version of that. Because we have collected both human motion and object all together, we can also get their contact information. We can infer that, and we can also get the affordance information as shown on the right side. They are basically the distance from the object and the fingers. So for the remaining time, let me just very briefly show some of our result. So you can see some sequential actions human performed given a instruction. So you can see clearly there is just some orders in behaving something, right? We open something, the door, place the item, we close the door, we turn on the stove, open the lid, and so on and so forth. So compared to basically the existing kind of motion capture data, our data has this kind of interesting sequences, and hopefully we can model such things by learning-based method. This is another example. One very interesting thing is obviously how given the same instruction, people's behaviors are quite different each other. So this one is pouring water from the kettle to the cup. The way to behave the motion is quite different. And hopefully we will also want to capture this kind of diversity from the model. This is put the laundry in the washing machine. You can see the posture, the timing, the order of opening the door. They're quite different each other. Cut the food on the cutting board. Again, they're quite different each other. So we try to make all this annotation of every action, and some demo version is already available. So you can visit our website, Para Home. And hopefully the entire version will be available soon within hopefully this month. Because we have collected the entire world of the room setup, we can basically make any synthetic viewpoint. So this is synthetic egocentric view, if that is usable. Of course, there are just several limitations. This is from a single room, so there might be some diversity issue of the object and so on. So we are building some augmentation skills so that we can diversify that. Another obvious direction is to make this kind of version room in many different places so that we can have diverse places, but that part would be harder. But yeah, so these are two different directions. So hopefully we can achieve both goals. Long-term in the wild motion capture from lightweighted mocap system. And another direction is more accurate human object interaction capture in a room setup so that we can have both paired text and action data. So that's it for my talk. So all this work has been done from my amazing group. Our group is actually very young. It's just 2 years only, but we already made really nice progress, and hopefully we can show more interesting one in our later years. Thanks a lot for your attention, and sorry again that I cannot be there in person. I'm happy to take any question if they have. Thank you.
Thank you, Hanbyul. We have time for maybe 1 or 2 questions. And meanwhile, we invite all the spotlight presenters to line up in the live site. And you can see the order of the lineup in the website. Yeah. And does anybody have questions?
Yes, Tao, I can hear you.
Okay.
Do you plan on handling the objects that are not explicitly modeled? For example, like cutting, I don't know what the person was cutting or like what they were doing. How do you plan on?
I'm sorry, I cannot hear the audience.
I will repeat.
Repeat, please. Yeah.
I guess the question is, how are you going to modeling the objects that is, I guess, not rigidly contacted or is contacted? So for example, if you're cutting some objects, and do you need to model every aspect of this cutting process, or pulling what, when you're modeling pulling waters, do you need to modeling every particles of the water?
Oh, okay. So the question is, if the target object is rigid or rigid articulated object, we can model it. But what if the model is not a rigid object? Is that the question?
Yes, yes.
That's something we cannot solve, obviously. So our first goal is to handle rigid object and articulated object first, and maybe we can handle the later one in a later time if there is any method. But even though we only target the rigid object only, still the target problem is, I think, challenging enough and the big enough, because if you actually see the behavior in your home activity, the tools we are using, they are mostly rigid, although, the food and this part may not be rigid. So our hope is maybe we can solve the rigid part first, and we can move on to the next time. But that's really amazing future work, yes.